Hello, today I solve classroom assignments, and first exercise is exercise 5, and we need to find Q and R. And in A equal to 5,286 and B 19. And we have two formulas. A formula is B multiplied by Q plus R. Q formula is divided A by B, and R formula is A minus Q multiplied by B. And we find the first Q, and so 286 divided 18, and we round it and have 278. And after this we find L, 5,286 minus 278 multiplied by 19, and this is equal to 4. And in division algorithm, R remainder must be between the 0 and B. R will be equal to 18, and exactly 4 is between 0 and 19. I'm sorry. And in B, we have negative 5,086, B equal to 19, and find the Q. We have negative 278, and find L. And R equal to negative 4, and our reminder R can't be negative 4 because there must be between 0 and 19. And to fix it, we subtract 1 from Q, and our Q after subtracted equal to negative 279, and we use the formula A to find R. Negative 5,286 this is equal to negative 5,301 plus R, and R equals to 15. And we fixed it and have positive equal results, and our R equal to 15 and Q negative 279. In C, we're given A 5,286 and B negative 19, and B is negative, and the remainder R condition uses the absolute value of B, and absolute value of B equal to 19, sorry, and we find the Q and round it to 278, and find R equal to A minus Q multiplied by B, and this is equal to 4. And after this, we use the A formula to keep the same remainder, and use the negative divisor, and we changed the sign of the Q, and after the positive we have negative 278, and we plus the remainder equal to 4 and have the same results 5,286, and this is equal to the same result 5,286, and our answer is R equal to 4 and Q equal to negative 278. In T, we're given A, negative 5,286, and B, negative 19. B is negative, and we use the absolute value of B is equal to positive 19. We find the Q, and after the round, it is equal to 278, and the after this we find the R equal to 4, and we directly apply the sign and use negative sign of B, and after this we have negative remainder, and remainder equal to negative 4, and to fix it we use the A formula and add 1 to the Q, and after the add 1 we use the formula, we have the result R equal to 15, and our result is R equal to 15 and Q equal to 279. Next problem 12, part E. We are given A 1,575 and B negative 231. And I start by applying the Euclidean algorithm. I divide the larger number by the smaller one and continue until the remainder is 0. I started. And this is equal to 231 multiplied by 6 plus 189. It is and the last one 42 is equal to 21 multiply 2 plus 0, and the last non-zero remainder is 21, and so the greatest common divisor is 21, and I will write short GCD of two numbers equal to 21. And now I express the GCD as linear combination. I start from the equation where the remainder is 21 and substitute backwards. 21 equal to and last one 21 to 5 minus and since b equals minus 221, I apply 221 with minus b, and b equal to and 21 equal to 5a plus 34 B. Yeah, this is the answer. And next one, G. Part G, we're given A, negative 3,719, and B, 8,416. And I applied the Euclidean algorithms again, step by step, dividing, and I started. And the last non-zero remainder is 1, and so get the GCD is 1. And using back substitution, I expressed 1 as a linear combination of the given numbers, and right there, 1 equal to minus. And A is, I write there 1 equal to we have the negative A, and this negative sign is signs of A, and I'm just write it positive 267 A plus 118 B. This is the answer of exercise 12, E and G part. Next, problem 17, and we need to find the x and y. And linear differential equation has integer solution if only the greatest common divisor of the coefficients divides the c. And I'm started to find the greatest common divisor of the coefficients, and I'm just continue. and the last non-zero remainder is 1, so the greatest common divisor of this coefficients is 1. And since 1 divides 4, integer solution exists. And using back substitution, I found one particular solution is x equal to negative 4,700 and y equal to 14,932. The pair satisfies the equation. Now we move to part B. The equation is 154x plus 260 y equals 4. And again, I start by finding the greatest common divisor of the coefficients. And greatest common divisor of these coefficients equal to 2. And now I check whether 2 divides 4, and yeah, it does, so integer solution exists. And one integer solution is x equals minus 5 and y equals 3. If we substitute the solution values into the equation, we get 4 on both sides. We move to part C, and we have equation 154x plus 260y equal to 3, and the coefficient same with part B, and the greatest common divisor is still 2. And we check that 2 divides 3, and it does not, and therefore no integer solution exists, and we don't have solution. And next part D, equation is equal to 196x plus 260y equal to 14, and we find the greatest common divisor of 196 and 260, and this is equal to and greatest common divisor equal to 4. So the greatest common divisor we find, and now we check whether 4 divides 14. It does not, so there are no integer solution, and we don't have solution. Next problem, section 3, number 1, and we need to find a number prime or not prime. And a prime number is a natural number greater than 1 that has exactly 2 positive divisors, 1 and itself. To determine whether a number is prime, we check whether it can be divided by any integer greater than 1 and less than or equal to its square root. First one, 157, we test divisibility by the prime numbers less than the square, and it's if rounded equals to 12.5, such as 2, 3, 5, 7, and 11. None of these numbers divide 157 57 evenly. Therefore, this number has no divisors of 0 than 1 and itself, so it's prime. Next one, 9831. We first check divisibility by 3. For this, we need to find the sum of the digits, and sum equals to 21, and 21 is divisible by 3. It means that this number also divisible by 3, and therefore 9831 has more than 2 divisors and it's not prime. And part C, 9833, and we test divisibility by small prime numbers such as 2, 3, 5, 7, and 11, and also etc. The number is not divisible by any of them, and no divisor less than this square root, because the square rounded equals to 99, and so this number is prime. And part D, we need to find the sum of these digits, and sum of these digits equal to 24, and 24 is divisible by 3, and it means that this number also divisible by 3 and is not prime. Part E, number of the form 2 to the power n's power minus 1 are called Mersenne numbers. And Mersenne numbers can be prime only if the n of n is prime, but even then it is not always prime. Since this number, it's not prime because this is the sum of this divisible by 3, and it's not prime. Next problem, 17, and part A, describe those natural numbers n for which t at n equal 2. And number has exactly 2 positive divisors if only if it is a prime number. So its 2 divisors are always 1 and the number itself, and in conclusion all natural numbers n with t at n equal to are prime numbers. And describe all natural numbers for which t n equal 3. A number has exactly 3 positive divisors only when it is a square of a prime number. If, for example, n equal to p squared, where p is prime, and then the divisors are, for example, 1p and p squared, and that gives exactly 3 divisors. And all natural numbers in conclusion n with t at n equal 3 are of the form n equal to p squared, where p is a prime. Next problem, number 3, section 4. To find a mod n, we divide a by n and take the remainder. Remainder must satisfy between 0 and n, and a formula equal to n multiplied by q plus r. And part B, we are given a 1286 and n 39. We divided it and have 32, and after finding remainder equal to 38, and the remainder is 38, and so the results modulo 39, and this is the answer. Part B, we are given a equal to 43,197 and n equal to 333, and we need to find q. Q is equal to a divided by n equal to, after the rounded, 129, and we find the remainder equal to 2440, and this equal to and answer equal to 240. In part C, we are given A and N. We find the Q by divided A by B and have the negative remainder minus 10. And by the remainder must be non-negative. So we added N to remainder and have 41. And answer is part D. In part D, we have A and N equal to 125,617 and N 315. And we find the Q and divided A by N. And equal to 398. And remainder equal to 247. And remainder is negative because we have the negative A. And after this, we just add N to have a positive number. And this is equal to 68. And answer equal to 68. Problem 3, part E. We have a large number and the number is made only of ones, and we can split it on 12 blocks of 4 digits. Yeah, 1, 1, 1. And each block is divisible by 1111. And so let us divide this 1111 divided same number 1111 is equal to 1, and it means remainder equal to 0. From 7 part A, we are given A, B, and A equal to 4003, B equal to 127 negative, and N equal to 85. When we working with modular arithmetic, we always reduce numbers model N first to make calculation easier, and our remainder must be between 0 and N. We reduce A modulo 85, and we divided A by N, and Q equal to 47. After this, we find the R remainder equal to 8, A equal to 8. And after this, reduce B modulo 85, and because B is negative, our remainder to negative 2, because Q equal to 1 when we divide it by N. And to make our remainder positive, we add to remainder N, and negative 42 plus 85 equal to 43, and our remainder equal to 43, and B also 43. And after this, we do calculations, a plus b equal to 51, and since 51 is between 0 and 84, this is always is a reminder, and a multiplied by b just value equal to 344 when we find the q equal to and divided this multiplied by n equal to 4, and remind also equal to 4. And last one, square of calculations equal to 2601, and when we find the q and divide it by 85, this is equal to 30, and reminder equal to 51. Next problem 9, and in this problem we are asked to find all integer x such that between 0 and n, and consists of the form ax equal to b modulo n, and has solution only if a greatest common divisor of a and n divided by b. And part A, 3x equal to 4 modulo 6, and we compute the greatest common divisor of 3 and 6, and they're equal to 3, and we check that whether 3 divided 4, and it does not, and we don't have any solutions. And part B, 4x equal to modulo 6, and we need to find the greatest common divisor between 4 and 6, and they're equal to 2, and 2 divides 2, solution exists, and we divided the entry carries by 2, and they're equal to 2x 1 modulo 3. Now we test the values of x between 0 and 2, and 0 can't be the value, and x equal to 1. 2 multiplied by 1 equal to 2, and x equal to 2. So the solutions modulo 3 are 1 and 2. Now I convert them back modulo 6, and finally answer is equal to x 1 and 4 of the part C, and we're given for x equal to 3 modulo 7, and we need to find the greatest common divisor of 4 and 7, and this is equal to 1, and since the greatest common divisor is 1, 4 has a multiplicated inverse modulo 7. And multiply both sides by 2, and equal to x equal to 6 7. Find the x between 0 and 7. The solution equal to x equal to 6. And part D, last one, for x equal to 3 model 6. And we need to find greatest common divisor between 4 and 6. This is equal to, and since 2 does not divide 3 and they not have solution. Next problem 22 part B. We are given P 20,593 and P is a prime number. We must find the 53 on the power 20,000, 50, 92, 93 and 94 modulo 20,593. And when the modulus P is a prime number, the following rule is true. A power to P minus 1 are always equal to 1 modulo P. This is so always true if it's not divisible by P. P equal to 20,000, 593 and P minus 1 is equal to 20,592. And because P is a prime, we immediately know that 53 in power 20,592 is always equal to 1 modulo 20,593. And the first one is equal to this. Now I increase the exponent by 1 because 20,593 is equal to the same 1. But we already know that 53 in power 20,592 is equal to 1, and it means that is equal to 53. And second one is equal to 53 model 20,593. And the last one is equal to 53 20,594 is equal to 53 squared multiplied by 53 20,592. This is equal to 1, and it means that this is equal to just square of 53 and equal to 2,809 and equal to this. Problem 18, part A. In each case, we must find the smallest non-negative and integer x that satisfies both congruences at the same time, and find the smallest x, and x must be more than or equal to 0, and that satisfies both congruences. And we are given x equal to 3 modulo 5 and x equal to 4 modulo 7. And first I find the numbers that are congruent to 3 modulo 5. And this is 3, 8, 30, 18, 23, 28, and etc. Now I check which of these numbers is congruent to 4, model 7. 3 is not, 8 is not, 13 is 6, yes, no, and 18 equal to 4, yes. And the smallest number that satisfies both congruence is 18, x equal to 18. And 18 part C, we are given x equal to 3 model 8 and x equal to 7 model 8. The first one model is 5, I'm sorry. And again, I list number congruent to 3 model 5. It's equal to 3, 8, 13, 18, 22, and etc. Now I check which one is congruent to 7 model 8, model 5, and 3 is no, 8, no, 13, 5, no, 18, no, and 23, yes. And the smallest non-negative solution is 23, x equal to 23. While listing solutions of the first congruence and checking the second one, we find the smallest one. Solution in part A is x equal to 18, and part C is equal to 23.